Okay, today we will be talking about constraints and how we can define constraints in our direct stiffness solution. So let's first write the definition. Constraints enforce a relationship among degrees of freedoms. Okay, now we can just classify the constraint definitions as follows. We can have constraints at structure level. Okay, and we actually define these relationship between the degrees of freedoms before, and the main, for example for that is the axial rigidity, right? So we take a structure like this, a very basic frame, let's say that point A, B, C, and D, and let's show all the degrees of freedoms. I got Bx, By, theta B, Cx, Cy, and theta C. Okay, so in order to impose the axial rigidity condition, we said that By is equal to 0, and also Cy is equal to 0. So here, as you see, I'm defining a relationship for these degrees of freedom. Okay, these are called single point constraints. Okay, I'm forcing the solution to give me 0 deformations at By and Cy. And also, in order to define again axial rigidity, I was saying that Bx must be equal to Cx, right? That's what we called a multi-point constraints. Now I got 2 degrees of freedoms, Bx and Cy, and I'm defining a relationship between these 2 degrees of freedom. And also I'm enforcing the solution to give me this relationship. Okay, so that's one example, the axial rigidity. We will see the methods to impose these constraints on the solution, and with this methods you can actually impose any other condition in the solution. We do it for this is the imposition of the constraint equations at the structure level, but we can also use these type of relationship in the element level, in the element formulations. Okay, and one of them is, we haven't discussed it yet, but we will, is the rigid and offsets. Let's say that I have a member here, okay, but I want some portion of these member ends to behave rigid. Okay, these parts are rigid part of the member, and this part is the flexible part of the member. Okay, and in order to impose this condition, this is what we do. We will have the rigid portion, we divide the structure into pieces. We say that our element composed of 3 pieces. Okay, and we will have some degrees of freedoms here, u1, u2, and u3. Let's say that the length of this one is equal to m. At this node, I should have the same degrees of freedom, u1, u2, and u3. And here, I will have different degrees of freedom. Let's call them this one to be u1 hat, this one to be equal to u2 hat, and this rotation to be equal to u3 hat. And then I define a relationship between these degrees of freedom and this ones. Since that's a rigid member, we can write the following relationship. u1 must be equal to u1 hat, right? There is no deformation. Since this is rigid, even though there could be any axial load on this member, since this part cannot deform, this part should be rigid, so this displacement must be equal to that one. Okay. Now, rotation, if I have a rotation that's equal to u3, this should remain straight, no deformation. So this rotation at the end of that rigid member should be equal to this one. So the other relationship that I can write is equal to u3 is equal to u3 hat. But the story is different in the vertical translation, because this point can translate. This must translate by the same amount, plus since I have a rotation here, I should have this additional translation. Okay, so u2 must be equal to u3 hat, sorry, u2 hat plus u3 hat multiplied by the length of the rigid portion. So as you see, if I want to formulate an element like this, the first thing that I will do is to write a relationship between the degrees of freedom and impose these relationships in the stiffness matrix calculations. Okay, we will talk about that in the upcoming classes. But here, what I want to do, let's say that I have the following relationships, okay, between different degrees of freedoms. How can I impose this condition in the solution? Okay, so there are actually three ways. So methods of imposing constraint equations in the solution. So we have three ways, and within the scope of this class we will talk about the first two. The first method is transformation. The second method is penalty functions. And the third method is using the Lagrange multipliers. Okay, now let's see how we can impose constraint equation by using the transformation method. While explaining that, I will be using an example problem. Let's say that I have this cantilever and I'm dividing this cantilever into three pieces. Each of them has length equal to L. And I'm applying an axial load that's equal to P. Another axial load here that's equal to P, and another axial load here that's equal to P. Now let's say that, assume that each member has an axial rigidity equal to K. Let's label the points. Now calculate the displacement at point 3, assuming that U2 is equal to U3. Okay, now here I'm imposing a multi-point constraint, right? I'm enforcing this deformation and this deformation to be equal to each other. This is basically, we are saying that this member is axially rigid, okay? But let's forget about the axial rigidity now. I want to analyze that structure, and I want to, at the end of the solution, I want to have these two degrees of freedoms equal to each other, okay? Now, our stiffness matrix for this structure will be 2K minus K, 0, minus K, 2K minus K, 0, minus K, and K. And the force vector, of course, will be equal to P, P, and P. Okay. All right, so our first step is this. The constraint equations in that case it's U2 minus U3 is equal to 0. That's my constraint equation. Can be written in the following form. Right, C times U is equal to Q. Let's call this one equation star, okay? So this matrix and this matrix contain constraint equation constant. Okay, so let's write it for this specific example. I got 3 degrees of freedoms, right? So I have nothing related to the first degrees of freedom, that's 0. The coefficient of the second degrees of freedom is 1. The coefficient of the third degrees of freedom is minus 1. Multiplied by the displacement vector U1, U2, and U3 is equal to 0. Okay, it's not equal to a certain value. Okay, the independent degrees of freedom in the system are U1 and U2. Okay, U3 is a dependent degrees of freedom since its value depends on U2. So, having that information, let's partition equation star so that the retained degrees of freedoms are only the independent ones. So I will partition it this way. I got CR here, CC here, okay, UR and UC here, and that's equal to 0, right? So in this particular example, let's rewrite the equation star one more time. 0, 1, minus 1, U1, U2 and U3 is equal to 0. So the first two degrees of freedoms are the ones that I want to retain. They are the independent degrees of freedom. So I'm partitioning it this way. Okay. So this will be the CR matrix. This is CC matrix. This one is UR vector and this one is UC vector. Right? Now, CR, I'm multiplying this with this one. CR times UR plus CC times UC is equal to 0. Then in that case, UC will be equal to minus CC inverse multiplied by CR times UR, okay? And I'm calling this matrix as our RC matrix. Okay? Then I have the following relationship. UR times UC will be equal to a transformation matrix multiplied by UR, and in that case the transformation matrix will be equal to identity matrix multiplied by CRC. Okay, so let's put it in our pocket. So we can say that similar partitioning can be applied to the equilibrium equations and let me write the stiffness matrix as follows. And in the stiffness matrix, I'll have KRR, KRC, KCR, and KCC. Okay? That's the way we partition the stiffness matrix. Now we said that U is equal to a transformation matrix times UR. Okay. Now I did the transformation in terms of the displacements, but you can write the same thing for the forces. We will discuss that later. T transpose times F. Let's call this so that these are the constraint ones. Okay. And the constraint, since we have the following relationships, remember our rotation matrix derivation, the constraint stiffness matrix will be then equal to T transpose multiplied by K multiplied by T. Okay, that's the constraint stiffness matrix. So my K prime matrix will be then equal to, the transformation matrix is I times CRC transpose multiplied by KRR, KRC, KCR, and KCC. And I will further multiply it by identity matrix multiplied by CRC. So at the end of the day, my constraint matrix will have the following form: KRR plus CRC transpose multiplied by KCR plus KRC multiplied by CRC plus CRC transpose KCC multiplied by CRC. And this will give me the new constraint stiffness matrix. Okay? Now you will better understand when we go back to our example problem. Back to our example problem. Okay, so our CRC matrix will be equal to 0 and 1. Right, how do we obtain CRC? Let's come back here. In our case, CC is equal to -1. Okay, so CC inverse times CRC, I have minus here, will give me the same CRC matrix as follows. Now let's write the K matrix here. I got 2K minus K, 0, minus K, 2K, minus K, 0, minus K, and K. Okay? So I'm partitioning this matrix. That's KRR, KRC, KCC, and KCR. Now, our constraint stiffness matrix will be equal to KRR. Let me write KRR now. 2K minus K minus K and 2K plus CRC transpose, which is equal to 0 and 1, multiplied by KCR, which is 0 and minus K, plus KRC 0 minus K multiplied by CRC 0 1 plus I got 0 and 1 here multiplied by K multiplied by 0 and 1. So when you do all these matrix operations, we obtain K prime as equal to 2K minus K minus K and K. That's the constraint stiffness matrix. Now I have to calculate the constraint force vector, right? And for that I need the transformation matrix. So I got 2 degrees of freedoms. So I have the identity matrix here and the constraint C matrix or CRC matrix in here. Remember that for the F prime we will be using the transpose of the transformation matrix, which is this one, and I have to multiply it with the force vector P, P and P, and when you do that we obtain our new force vector P and 2P, and the result, or let me write it this way, the solution I got 2K minus K minus K and K. Now I got only 2 degrees of freedom, U1 and U2, and I have this new force vector P and 2P. And the results are as follows. U1 will be equal to 3P over K, and U2 is equal to 5P over K. And that's the result. Let's check if this makes sense, right? So what we are doing here is, let's go back to that problem again. This is axially rigid, right? If this is axially rigid, it doesn't matter if I put the load in here or in here. So I got 2 degrees of freedom, the first and the second. The first P is applied to the first degrees of freedom and 2P is applied to the second degrees of freedom. So this force vector makes sense, this one. And this is a rigid frame. If we forget about this frame, just forget about this. This one will have K stiffness, 2K stiffness, right, to move in one direction. And this one will have the stiffness that's equal to K. And this stiffness matrix is also makes sense, and these are the final results. Of course, this is a very simple example. We can guess the solution without doing all these calculations. We can analyze it, but consider this as a method, and once you have that relationship, or once you write this equation by following that procedure, you can obtain your transformation matrix. If you know your transformation matrix, you transform it, obtain your new stiffness matrix, displacement vector and force vector, and this will give you the constraint solution. Now let's take a look at the second method for imposing the constraint equations, which are called penalty functions. So in order to do the derivation, first say that let's write the constraint equations in the following form. T is equal to C times U minus Q, and let's call this one as our equation 1. We say that the constraints are satisfied if this vector is equal to 0. Okay, so we satisfy all the constraint equations if this part is equal to 0. Now, let's write the total potential energy of the system. Of any structure in static equilibrium is as follows. And I will write it in matrix form. So the potential energy is equal to 1 over 2 U transpose times K times U minus F, right? So let's take a look at this equation. That's the internal elastic energy, right? And this is the work done by the external forces. So for this, I'll just draw this figure just to remind you. So this is the internal energy, and that's the displacement. And we see a relationship like that, right? And the magnitude of that is equal to K times U. I'm just doing it for a single degree of freedom system. And energy, the strain energy, is the area under this triangle, which is 1 over 2 times K times U, right? So I just write it the same thing for a multi-degree of freedom system. That's the internal strain energy. And this is the work done by the external forces. Now what I'm going to do is add another term to it, plus 1 over 2 T transpose alpha times T. Okay, so this one, diagonal matrix of penalty numbers alpha. Why did I do something like this? Now, if these constraint equations are satisfied, right, T would be equal to 0, and I wasn't adding any additional energy to that system. Okay, if you don't satisfy it, and if I put a big number here, I will just penalize not satisfying this equation by adding additional energy to the system or by disturbing the equilibrium condition. All right, so let's write it down. So we are saying that in equation star, if all the constraint equations are satisfied, which is said by T is equal to 0, constraints are satisfied, and no additional energy is added to the system. The other condition, if you don't satisfy that, if the solution that we obtain doesn't satisfy that, So we are saying that penalty of the constraint violation becomes more dominant depending on the value of alpha. Okay? Now, so I want to have this to be minimum, right? So that the equilibrium condition is satisfied. Okay? So what I'm going to do is this. I want to have the total potential energy to be minimum. So in other words, the derivative of this potential energy with respect to displacements must be equal to 0. So that's the condition. Okay, I want to have this to be minimum. So this is the condition of having that equation to be minimum. Okay. This is the minimum energy condition. And inserting equation 1 into star, we get the following relationship. 0 is equal to K plus times C multiplied by U is equal to F plus C transpose alpha times Q. Okay, just think about this way. If we don't have this term, what we will get at the end of the day will be our equilibrium condition. The equilibrium condition will give us the minimum potential energy for this system. Now I add this additional term and I'm trying to make that term make this t equal to 0 so that I still satisfy this condition, and this should give me the forced degrees of freedom, the values of the degrees of freedom in such a way that they will satisfy the following condition. Let's go back to the example problem again. Back to the example problem. Remember that my constraint equation is written as follows. C is equal to 0, 1, minus 1. And Q is equal to 0. And my alpha matrix, I just write it in this way, alpha multiplied by the identity matrix. Okay. Then I'm writing this equation now. I shouldn't be showing this way because I already play with that equation. Okay, I got K. K in our case is 2K minus K, 0, minus K, 2K minus K. That's the stiffness matrix. Plus alpha is a value that we will define. 0, 1, minus 1 multiplied by the identity matrix multiplied by 0, 1, minus 1 Okay, multiply with the displacement vector u1, u2 and u3 should be equal to the applied force vector P, P and P. When you perform this operation and add it with the stiffness matrix, our new stiffness matrix will have the following form: 2k minus k, 0 minus k, 2k plus alpha minus k minus alpha, 0 minus k minus alpha, and k plus alpha. u1, u2 and u3, that's equal to P, P and P. Okay, and if you solve this system of equations, this is what I obtain. u1 is equal to 3p over k, u2 is equal to 5p over k, and u3 is equal to 5p over k plus p over alpha plus k. Alright, so here I work symbolically. Now let's say that alpha is equal to 10k, then my u3 becomes equal to 56 over 11p over k. Okay, let's give a larger number. Alpha is equal to 100k. In that case, u3 will be equal to 506 divided by 101 p over k. Alpha is 1000. I'm just keep increasing alpha. As you see, I'm converging to the solution that I want to impose at the beginning of the problem. So as I increase the value of alpha, I'm penalizing not having these two equal to each other, right? I'm penalizing more. The more I penalize, the closer solution that I obtain. And that's another method of imposing a relationship between different degrees of freedoms.